presentation, we can proceed to the lunchtime. It will be over there. We will open the door and you can go have the lunch all together. Thank you.
So hello everybody. So I will be the conveyor of the session. So the first speaker will be Miklos. He presented him this morning, but I would add that he's a managing director and associate partner of both GPC instrumentation process and Geofluid, and his associate is Pierre Ongemar. One of the Pope of Geothermal, with Latsy Rybak, for example. Yes, Latsy is a god. And I am an angel. And the specificity of Miklos is that he's a big expert for the Pannonian Basin because he's born there. So that's very important to tell you. And you work there also. So I leave it. Yeah, I leave the floor.
Thank you, Christian. Yeah. Can I borrow the microphone? Yes. Okay, use the pointer. Yes, ladies and gentlemen, good afternoon. Well, this is the most difficult time. And 9 out of 10, my talk is always in the afternoon. So those who want to sleep, I don't mind. I understand you perfectly that yeah, it's normal after lunch to have a short break. But I try to entertain you, this for those who are still awake, with a topic which addresses development of geothermal energy in areas with low transmissivity and high density of population. And this is a bit the case of the development. We have heard a lot speaking about the Paris. What do you want to do?
Juste le pousser parce que sinon vous êtes trop devant. Ça va? Merci, merci.
If not, I can sit here and I don't. And then we have heard a lot about the Paris Basin geothermal district heating. Virginie said is one of the largest in the world. Very few people know it. We don't make enough publicity about geothermal. I was speaking to Josephine. We should speak about geothermal in the morning, at midday, in the evening, every time, every day. TF1 or France 2, the French public TV, should give a documentary on French geothermal to the audience, so geothermal becomes desired, as it is in Paris. I'm going to address a bit the well architectures, because this is the key to solve production, right? Large production issues in low transmissivity area. And these are three well architectures on which we have mastered the first one on 2 projects. This one we just designed it, but we did not execute it. And this is a new design. It's an extreme extended reach multilateral or stacked multilateral. Now we come to the conclusion. Well, this is a bit a map which was done by my colleague, Gillian. Of course, the numbers here of the district heating sites which are printed and operated may differ from those presented by Virginie, because their report came after our study. So we have today this study has been published in February 2024 in Stanford, the paper. And at that time, we had 52 doublets in operation, and we expect in 2030 to have 80 in operation in the Paris area. And the heat, the energy we produce is 1,600 gigawatt thermal per year. And then what we expect to double this capacity, which is true according to the forecast which was presented both by the government and by the association. What you can see here, these blue pills, don't think of other things. These are protection areas of the geothermal doublets. That means that when you site a new doublet, you are not allowed to drill in this protection perimeter. Now it's questionable, because we are getting to places in the Paris area. These are all cities around Paris. We have a place where we can site our doublet, the wellhead, which fits in this blue area, which is the perimeter, but the impacts of the wells will go outside. So this is a bit questionable, and this should be addressed by the authority to us. How can we site a wellhead within the blue perimeter and drill outside the blue perimeter? Well, for this situation, I'm going to talk about two projects which we achieved. The first project is in Cachan, which was operated since 1984 with two doublets. Both were producing 350 cubic meters per hour. That means 4 wells. And then the idea was to renovate these doublets because these got old, and then it cost a lot of money to repair them. And the municipality asked us, what can we do? Is there a life after? Which is rather a metaphysical question than an engineering question. So we had to come with an engineering solution. And instead of drilling 4 new wells, we designed 2 wells to satisfy the objective of 350 cubic meters per hour. Why we had such a low productivity at that time? Because we are in the transmissivity area which is rather low, which is below 10 Darcy meters, and these wells were drilled from the same platform, deviated, and then the surface captured by the reservoir was rather low, and this was the productivity of the wells, 170 cubic meters per hour per doublet. So we have designed, and what we could see that you can see in light blue, it was the surface which was covered by the 2 doublets, and in this pink, it is the surface which is covered by protection perimeter, which could fit it right into the existing ones without interfering with the neighboring doublets too much. And then the second project, it was in south of Paris, in Grigny. And in Grigny, unfortunately, we were in charge with the well construction support in 2016, and we inherited the project with the wells already placed, with a permit already awarded, and we wanted to change the impacts, but they said, no, you have to drill where the authorization is. And we lived the first geological failure since years, because the injection well was not so good. So we had to design quickly. We had to design quickly a new injection well in order to satisfy the needs of the doublet. So, of course, this area you can see is less dense. And then there was a second project in Grigny which has been set, and again in an area which is with rather low transmissivity, below 9 Darcy meters. And of course, we immediately, after the first experience in Cachan, where we have sited subhorizontal doublets, a subhorizontal doublet, we have sited another subhorizontal doublet in the Grigny area. And in order to avoid any geological failure and satisfy geothermal flow rate objective at 450 cubic meters an hour. Well, this is how about geothermal looks like. At least if there is no rig on the site, nothing is visible. Oops. This is a site which is again in south of Paris, in Épinay-sous-Sénard. You can see that the wellheads are in the park. The heat plant is below in the parking, and you have some sort of castle, which is a town hall. But when you walk in there, you have no idea that there is geothermal heating all the buildings all around. Well, when is a rig on site? This is the Grigny site, and this is the Cachan site. It was really downtown in the city. We had the neighborhood with a big tower, so noise and nuisance was quite a challenge. And then here is in Melun-l'Allemand, which is a highly density traffic zone on which we have designed a new production well recently. So I'm focusing on why should we go for a new generation of wells. When we started geothermal years ago, we have drilled 2 vertical wells. One vertical well here, and at the 1.2 kilometer, another vertical wells. This was the project of Le May-sur-Seine. What is it? Ah, okay. Yes. Yeah, I'm sorry. Yeah, and then we have moved from one vertical to one deviated. This was the second generation well. Usually the injector was more deviated than the producer. Then we came to two deviated wells from the same platform. Why do we do deviated wells? Because we have no space where to put them in one place in the city and another place in the city. So we have to drill them from the same platform in order to achieve a spacing at the reservoir at 1.5 kilometers. Then we have thought that the fourth generation of wells will be the subhorizontal, which will cut on a high angle at a long distance, about 1 kilometer, all the layers. And the fifth generation will be the stacked multilateral or the planar multilateral. I'm going to go into details later on, which will go each drain in one layer. Why should we do that? To optimize land occupation, to challenge this permeability problem and transmissivity problem essentially, and of course maximize the captured length in the reservoir, and of course upgrade a bit the way we were evaluating the reservoir. And then what did bring us? We got innovation in terms of doing well architecture. We'd see horizontal wells. They have been drilled, so many. There are more than 180,000 drilled only on the North Sea. So why should we come with geothermal? Unfortunately, when we came with this project and we put it on board as a solution for the question of what should we do for the next period of exploitation, everybody said it is never going to work. Well, this is the reaction, when people are hostile, And then, well, we answered the question of sustainability, that we can continue producing geothermal energy for the next 30 years on the same site, so we can serve the community with sustainable heat. And then if we can increase also the capacity by drilling new wells, of course, it's a capex, we will say capex ratio, OPEX ratio reduction, because we drill only 2 wells, which will of course cost more, but it will cost less than drilling 4 wells. And then we also had to tackle the structural geology and how to appraise the reservoir, because we don't know much about, though we exploit it by so many wells, we don't know much about this reservoir, because we do not have the continuity between layers and between doublets. So this is again a challenge. So in terms of well architecture, the Cachan project was a rather classical project. We have drilled vertically about 1,000 meters, and then we started kicking off, and we landed on the top of the reservoir at high angle, at 84 degrees. And then we continued the horizontal drain in 1 kilometer in each well. The Cachan 2 well, at that time in 2018, was the longest ever drilled well in France, 3,010 meters drilled length. Well, for Grigny, we have changed the approach, because we have learned from this project the following, that using a steel completion, we will need to, that was essentially due to production constraints, we have to install a downhole chemical injection line, and because here we are at a very, we are at horizontal section, it is not going to be run by gravity and plus that line was a prototype with the fiber optics financed by EDEM. This was another innovation we brought into the project. Anyway, and then we have changed the design, so we did a double kickoff, and then plus Grigny, we did not have so many offsets like we had in Cachan, so we had to do a pilot hole on the first well to assess the layering structure in order to define the strategy of how to drill the horizontal drain. And this I will show you later how we did it. On the second well, we did not do the pilot hole, because we discovered that it's not really useful to do it. But here we did a double kickoff, and we landed at top of reservoir at 70 degrees, and then we did it with a sharp angle tool, the kickoff, and then we continued at 84 degrees. Well, this was a bit not what was in our mind, but was a bit the strategy of did we go from planning, from geological, from the pre-drilling model, from the well plan, the offset wells which we have considered. Then we have done our well plan. Then we have monitored it via tools, directional drilling tools, with logging while drilling. For the first project, we have deployed only azimuthal density and neutron porosity tools, which are, and then we have, in order to compensate the distance between the logging tools, logging while drilling tools, and the drill bit, we have done XRD, XRF monitoring, which gives you the mineral content of the cuttings you are getting. So you know that you are in the same phases, because the cuttings were coming back in 1 hour, and we were advancing in 9 meters an hour, and the logging tool was 15 meters behind when we were seeing the information. So we had to have a decision how to geosteer. Should we stay? Are we still in the same layer, or are we going to drop, or are we going to increase the inclination? And then, of course, if we reached the TD, we stopped. And then, of course, we did the post-drilling analysis, because that is always useful when you go and upgrade your planning of your second well. And of course, we have complemented, and this has been never done on geothermal well in France, in horizontal geothermal. First, the innovation was first horizontal, and then we have done nuclear magnetic resonance and sonic dipole, which we processed it for far-field sonic with SLB. I'm not paid by SLB, by the way, so I'm not making any publicity for them, but it was really a rewarding job. And then we have done well tests, and we assessed the productivity of the well. So based on that, we have done and then designed the second well, because you see the dip of the reservoir is going from west to east, and then we had to go with the second well uphill. So and the big challenge is this is the injector. Of course, as for the producer, we have cut all the reservoir layers, and we get maximum of them, and we got the objective flow rate. It was to have the maximum surface area exposure in the injection well to be able to re-inject the produced flow rate. So here you can see a comparison. I'm not going into detail on what is the influence of the angle and the dip and the angle on which we are geosteering on the length, effective length, captured length in the well. But you can see that this is an exaggerated image, and this is what we have done. We have done more than 40 changes in the bit, and we were geosteering in metric size layers. This is what the petroleum industry does. In fact, we borrowed all this knowledge from the petroleum industry to deploy it in geothermal in a carbonate reservoir, a multi-layered carbonate oolitic reservoir. We have had an open hole completion, so wellbore stability, it was not a question. We have done a geomechanical model in the team with SLB, so we were quite confident of doing this job. And this was the sonic far field processing. The same we have. This was done for Cachan. The same we have done it also for Grigny. And you can see that this sonic far field has the beauty of looking 40 meters around the bore, and you can see what is the continuity or the discontinuity of the particular layers you are looking at. And then this is the fact that when you drill a hole here and you have a layering structure, then if you move 100 meters or 200 meters far away, you no longer find the same layers at the same position in this structure. Well, this ended up also with papers, a lot of publications. Well, the innovative component of this project was financed by the ADEME, and it was quite rewarding because it led to this. Well, the second project, Grigny, when we did the first project, we had the resistivity tool, but we did not believe in it. I mean, let's say that also we learned a lot. And then Schlumberger came and proposed us the Periscope HD, which is a resistivity tool, which is very close to the bit, but we also, by conservatism, we have maintained the neutron porosity and the azimuthal density. So we in this well, we can see that we have found the first layer. We have steered for a couple of 100 meters, 200, and then we were again in a metric size layer for about 600 meters. We were steering in this layer. This is below the image. What if we would we would deploy the periscope edge, which is a high resolution tool, resistivity tool, which would give us much more precision in steering within this layer. Well, we did not deploy it because it was more expensive. One thing we have learned in geothermal, we do not have a check, a blank check in which you can spend a lot of money in the way we want. So we have to optimize and be creative all the time. And well, this was quite rewarding. The well I just give you, it was commissioned 2 months ago, and it exceeds the expectation. We planned it for 400 cubic meters per hour, but it would easily give 450 cubic meters per hour. So that was another rewarding exercise on doing geosteering. Now we have to move to the multi-radial well architecture, which was deemed to be an alternative to the super-horizontal. And then we have done whilst designing, we have compared the landing angle of the well compared to the surface the length drain, and also the pressure depletion we would obtain whilst producing. And we can see that if you land the well at 80 degrees, then we will have the less pressure losses, and we have the longest drain length by drain, and then we could have less interference. Well, there are many things written and there are many things non-written in geothermal, and those who are not written, they are the most penible things. People say we are not allowed to land your well at an angle higher than 60 degrees. It's not written anywhere. We have done it at 84 degrees, at 70 degrees. We can land it at 80, and we can do it this drain geosteered right. Well, this is it. We have not achieved this project as we designed it. A similar project has been achieved. 2 similar projects have been achieved by ENGIE, but doing them completely differently. Well, now we're coming to stacked to multilateral wells. Why multilaterals? Because as you could see from my first picture, that you would capture each layer of the reservoir, and you will steer in each layer of the reservoir. And here is a bit the classification of the multilateral well design. So you can see that there are serious ones. We would just be modest and stay with the standard dual lateral on this planar dual lateral, which will be the equivalent, let's say, of the multiradial. And then later we would go maybe for the fishbone architectures and things like that. Who knows? In the next what we will get on the table. And then this is a bit the well design. This is a second project in Grigny, which is north of the first one, and because there is one of the biggest district heating systems in south of Paris. They have a heat demand of more than 90,000 gigawatts thermal hour, if I'm not wrong. So this is why the ambition to have so many wells drilled by the same operator, which is the SER. And then this is what the well designed for the stacked dual lateral, and then we have done the same for the planar dual lateral. Again, we are in a very, very particular 9 decimeter transmissivity zone. Maybe we could get a little bit better for the production, but I'm not sure. It's still, from our estimates, it's not a good zone. This is why we try to maximize exposure by layer in this project. Well, we are, of course, at design stage. We have done reservoir modeling by different well placements and different grid structures in order to assess first the thermal impact and the pressure and the cooling kinetics in the wells, and also the pressure interferences with the neighboring doublet, which is at the north. And every solution looked well. Except this one, the planar multilateral would occupy a bigger space, of course, of cooling, but no cooling, no thermal breakthrough, neither with the neighboring wells, neither with the production well, and neither with the existing one. What we have learned by doing this exercise, well, we know that from doing a single planar subhorizontal well, we would get drawdowns between 11.3 and 12.3 bars, which are quite favorable. But these are from modeling. These values should be corrected with the effect of the drain. So if you correct them, you will still be below 20 bars. And then the injection, you will be at 16 and 17.5. And cooling kinetics, 0.2 degrees, so which are negligible. And then, again, the twin planar subhorizontal will give a higher cooling kinetics, as you could see it from the figure. But when we would go for the stacked multilateral, we would get even better drawdowns. I mean, more favorable. Lower the drawdown is, less electricity you consume, and more COP your doublet has. So for the same flow rate, you will increase dramatically the COP of your doublet. And then you will have the cooling kinetics of the stacked multilateral, because we are covering a large surface of the reservoir in there of 0.65. Then the twin stacked, that means we have two stacked planar multilaterals about 1 degree. So you capture even more in the reservoir. Well, if we go a bit comparative figures, because I think these numbers are those who are decisive for designing. For a subhorizontal, we master the technology. We can achieve easily 450 cubic meters per hour in a reservoir environment between 9 to 10 decimeters. We end up with a capex of 15.6 million euros. We have to land, of course, at a high angle in order to cover most of the surface. A particularity of the Dogger reservoir is that the first productive interval is just immediately at the casing shoe. So if you miss that, by landing too high and going then in a sharp angle, you will miss a large surface you will have to cover. So this is why we stick to our experience that we have to land at a high angle. Then, of course, the multi-radial, again, you have to land it with a high angle. It will cost almost about the same. You will achieve 350 cubic meters per hour from this well architecture, but the problem is that you will need, it's quite expensive if you want to stimulate each drain individually. You will have to run a cold tubing with a MLT tool, with a multidirectional tool to stimulate the right drain, right moment. And the multilateral, of course, it's more expensive because you will need to go in each layer and geosteer in each layer, but expectations for high flow rates are much better. And then as the geothermal grids are demanding more and more heat and more energy, this could mobilize, of course, more energy, but it's going to be more expensive, obviously. But it will pay on the long time. I'm not showing the project which we are going to achieve, which is going to be the FAR project of the year, in which we are going to complete all this subhorizontal with composite material, which is not going to be cemented. It is a patent we have done in 30 years ago, and we are going to deploy it now in the subhorizontal. Therefore, we will not need any downhole chemical injection line. Well, all these solutions are capable of satisfying high flow rates of in a rather low transmissibility reservoir, and they take advantage of all the experience gathered in the oil industry from tools, geosteering, BHAs, and also reservoir assessment. All these tools are available in the oil industry, and well placement technologies. Of course, they are expensive, but they benefit of important OPEX savings, which I said, because we are going to spend less electricity in running this project, and if we complete it even with composite, is not added, it will add almost €1 million to the bill. Then it will save even more on the OPEX of the well, and then it will secure operational safety and longevity and sustainability and security. Well, I used to conclude with this, thanking for your attention. I should add to my list of benefits of geothermal energy also is strategic energy resource, is strategic, renewable, sustainable, proven and realistic. Thank you very much.